it's hugely dominated by the centripetal, so it's basically, if you wanted to draw that to scale, it would be more like this. This would be 40 meters per second squared. This is 6 meters per second squared. So the resultant looks something like this, 40.4 meters per second squared. So you use Pythagorean theorem to get the length of the resultant, and how do you get the angle? What is it? Inverse tangent. And this angle would come out to be, I think it comes out to be quite steep, 81 degrees. Now that angle is just the angle between the acceleration and its tangential component. That's kind of a weird angle to give. It's not really that meaningful. What we probably would want to give is the angle between the velocity and acceleration. So there, that's just the supplementary angle, right? When two angles add up to 180. You guys call it a supplement? Yes? When two angles add up to 90, it's called a complement. Complementary angles. When two angles add up to 180, it's a supplementary angle. In any case, if I want to get this, I just subtract from 180. It's 99 degrees. So in this case, the angle between the velocity and total acceleration is equal to 99 degrees. And as we said, it should be more than 180, more than 90 if you're slowing down. And it is. It's 9 degrees more. Mostly inward, but slightly backward. So we're mostly concerned with holding the turn at this point with a slight bit of slowing the motion. Okay? So if we wanted to characterize what was going on at this moment, we'd say it's mostly inward to hold the turn, but slightly backward. So we are slowing down. And if we do slow down, well, of course, that means that our centripetal needs later are smaller, because the slower you go, the less you need to hold the turn as well. So if we go over here to the final, we can once again do Pythagorean theorem to get that total acceleration. That total acceleration is, work it out yourself, 6.5 meters per second squared. Much smaller overall, because of course our needs in the tangential direction are the same. We're trying to cause the same speed decrease, so the tangential hasn't changed, but our needs on the centripetal side are very minimal now. We're going slow, we don't need a lot to hold the turn. So our overall acceleration has decreased, okay? Our overall acceleration has decreased from 40.4 meters per second squared to all of 6.5 meters per second squared. I will leave it to you to verify that the angle between the velocity and acceleration, it is still more than 90, and in fact, it has grown to 157 degrees. It has opened up considerably. And the reason, of course, is that now most of our resources are against the motion, right? We have our fixed acceleration against the motion, and now that's 6 meters per second squared, and a very minimal 2.5 meters per second squared to hold the turn. So now we might characterize this as mostly inward, or sorry, mostly backward. Let's start in the same order as last time. So it's slightly inward and mostly backward. Now most of our efforts are placed towards continuing the speed decrease. We have very little effort necessary to hold the turn at this slow of a speed. Okay? So the angle is opening up. We're slowing down in both cases, but here it's 99 degrees, here it's 157 degrees because of the allotment of what's inward versus what's backward. Okay? And I should mention, by the way, that the overall acceleration started off at 40.4, ended up at 6.5. So that's, again, a little bit about allotment of resources when you're going in a circle. The faster you go, the more centripetal acceleration you need, and the faster you want to change your speed, the more ATAN you'll need. On your homework, you have basically a question like this in reverse. So instead of going along a circle and going slower, you have something going in a circle but going faster. You have a discus thrower. So discus thrower sticks something in a circle, let it going faster and faster and faster and faster, right? And they finally let it go. So if you've ever tried to throw anything heavy in a circle like that, what you notice is that at first, the hardest part is getting it going, right? You're focusing on ATAN at first. You don't need a lot of acentripetal because you're not going very fast. But by the time you're spinning really fast, it feels like your arm is being pulled out of its socket. And that's because you're having to have a lot of centripetal acceleration to maintain that circle. Of course, that's immediately relieved when you let it go. You don't have to provide acentripetal anymore. Any questions on that? Example or? Okay, so this right here closes out your homework 8. You have several of these kind of angular kinematics problems at the end. Building to the most challenging at the very end. If you're solid on those, then you can make sure you're solid on the concepts and calculations. And the next thing I want to do is see how far we can progress forward with homework number 9. Yeah.
So the final acceleration of the 6.5
So the size is 6.5 meters per second squared. That's from Pythagorean theorem of the two components. And then, of course, if I'm expressing the acceleration, I should also give the direction. So the direction is 157 degrees from the velocity. So technically speaking, if I wanted to express A initial with a vector hat, I should say it is 40.4 meters per second squared, and it's 99 degrees from the velocity, right? So that would be an appropriate expression of an acceleration. If I put this vector hat here, I should express the size and direction, right? Any other questions? Okay, so let's go ahead and move forward. We're at the same juncture now that we were before. In homeworks 1 through 3, we became expert describers of motion, we call kinematics. Now we've become expert describers of angular motion. We now enter the next layer of the onion, which is where does angular acceleration arise from? Well, it arises from angular version of force, which we call torque. So let's talk about that. And again, a lot of this stuff proceeds as just kind of a bizarro version of the stuff we've already done. So the easiest way to introduce it is just by showing it side by side. So force versus torque. Let's just compare and contrast. So force, we have an object, we apply a force, a net force, and that leads to this acceleration. And of course, at this point, we know enough to know it's really the only acceleration of one point, the center of mass. That's why we're introducing the torque for the rest of the object. So I should connect this to the center of mass. These two are always in the same direction. Whatever direction you apply the net force, the center of mass accelerates that way. And the law, of course, which tells us Newton's second law, which relates these, is F net equals ma. Which means, of course, that we also have to consider the object's mass. That object's mass informs us something about how it reacts to force. Mass is linear inertia. It's the quantity which measures how stubborn something is to the outside world. It's stubbornness to linear change. Literally, how stubborn is it to accelerate? So if something has a large mass, it won't accelerate very much. And likewise, if it has a small mass, it'll accelerate quite a bit more for a given amount of force. So these are just basics of Newton's laws that we talked about around homework 4. We introduced it and then ran with it. And of course, question? Sure. Yeah, I'm running a little smaller just because I'm hoping this is reviewed, but stubbornness to linear change. So we can, of course, even back it up one more step, Newton's first law, which is, of course, that if our net force is 0, then we don't have any acceleration, right? Things don't accelerate just because they feel like it. They have to be prodded to by the outside world. So that will mean that the velocity of the center of mass is constant. Which could mean one of two things. It could be constant at 0, which is at rest, or it could be some non-zero constant. And of course, so it could either the center of mass stays at rest, or it stays at a constant speed in a straight line. Constant speed, constant direction. So that's Newton's first law, which hopefully is familiar. And that's the only thing that can happen if you don't apply net force to something. The center of mass will either stay put, or it'll just keep going in a straight line at a constant speed forever. All right? So that's net force, and let me go over here if I'm going to write a little bigger. I need a little more room. So torque is over here now. You can continue to put it over on there if you don't have constraints. So let's talk about torque. Let's say I have a rusty bolt. If I have a rusty bolt and I want to loosen it, I have to angularly accelerate it. Let's say I angularly accelerate it like that. Well, that doesn't happen by itself. Something doesn't spontaneously angularly accelerate itself. It needs torque in the same direction. We sometimes call it a torque wrench. So if I want to angularly accelerate something counterclockwise, it requires a torque in the same direction. These are always in the same direction. So the net torque causes angular acceleration. If we wanted to write down Newton's second law, it looks like this. Very similar structure. Just like net force leads to acceleration, net torque leads to angular acceleration. And the third variable is the rotational analog of mass. It's called rotational inertia. It measures the object's stubbornness to angular change. How resistive is it to changing its state angularly? And it's the same basic deal if it's a lot stubborn. Then when you apply a torque, you'll get barely any angular acceleration out of it. So for a given net torque, a large rotational inertia means it barely angular accelerates at all, versus if it has a very small rotational inertia, it will angular accelerate quite a bit more. So what's the difference between rotational inertia and linear inertia? The difference is that linear inertia is synonymous with a single physical quantity. If you want to know how stubborn something is to linear change, you just need to know its mass. Here's the problem with rotational inertia. If you want to know how stubborn something is to angular change, there are no less than 3 different factors that you have to consider going into this. So this makes this equation, this Newton's second law in the angular world, a particularly difficult equation to tackle because it has 3 ingredients, of which 2 are brand new. We don't know about torque, we don't know about rotational inertia, so and we just saw angular acceleration. So it can be a daunting equation to tackle. But one of the ways that I will suggest tackling it is again by writing the equivalent of Newton's first law, where if the net torque is 0, then there is no angular acceleration. The angular velocity is constant. There, I can get away with not knowing about the rotational inertia at all. I don't need to know how stubborn something is to angular change if I'm not trying to make a change, right? I don't need to know about I if the net torque is 0. If the net torque is 0, I don't get any angular acceleration anyway. So I don't need to know anything about how stubborn it is to that angular influence. So what can happen? Well, the angular velocity can be constant at 0, which means you just stay not spinning. You stay not spinning. That's one thing you could do. Or, of course, you could stay at a constant speed, constant angular speed in a constant direction. So counterclockwise or clockwise constant. So it just spins at a constant rate. So those are the 2 things you could be doing in the absence of a net torque. You could just stay not spinning at all, or spin at a constant rate. Can't go spin faster or slower, or change direction spontaneously. Okay, so this right here kind of lets us focus on torque first. We'll kind of start with torque, and at first we'll make sure that all the torques cancel and the net torque is 0, and then later on we'll allow the torques to not cancel and tie it into the angular acceleration by discussing rotational inertia. Okay. So the first order of business, we'll tackle torque, and second order of business, we'll tackle rotational inertia. And when we've done that, that will close out homework number 9 and exam 2. Okay, so I guess in the next 3 minutes, let's see if I can get anywhere on torque. Probably not, but give it a shot. So torque. One object that you angularly accelerate every day multiple times is a door. You open doors. You take it from a state of rest and you angularly accelerate it so you can walk through it. Okay? Let's do a top view of a door. Here's the hinge. Here's the top view. And let's strategize about ways to open a door. Okay? So right now you don't have to know how to operate a door to get out of this room. But if you had to open that door, what would you do? Okay? Seems obvious how to open a door, but there's some stuff that goes into it. Ways that you can fail at opening a door. Okay? Let's try let's look at some door fails. Okay? You've never seen a door. Okay? Step 1, things that will not work. Okay? Pushing on the hinge. Okay? You will not open a door by pushing on the hinge. You need what's called leverage. Okay? If you push here you will not have very much leverage, and it's much harder. And if you push out here, which is where why the doorknob is here, you can angularly accelerate a lot easier, right? So you can talk about opening a door like this. That'll work. Force applied here, that'll work. This is better. You'll get more angular acceleration out of that. And of course, this would not work at all. The torque is 0. And by the way, I should mention if this is more angular acceleration, the further you apply it, it must be more torque, because it's the same door. So it's how much it resists rotation is not negotiable. And the factor that we need to actually measure is R, the leverage. It's the distance from the pivot that you exert the force. Okay? So R is the distance from the pivot to where the force is applied, force application point, or informally we call that the leverage, and more is better. Okay? There is also a way to fail in opening a door with a lot of leverage. Let me demonstrate. I can apply a lot of force at the edge of a door as far away from the hinge as possible and not successfully open it. Here is how. Okay, so if you can't see what I'm doing, I'm just pulling like this. Okay, so that will also be no torque. There, it doesn't matter that I get lots of leverage and apply lots of force. I get no torque. Of course, the reason why is that the force is entirely radial and not at all tangential to the circle that the door is constrained to move around, right? It's got a hinge. So we're going to have to consider the amount of force, the leverage, and something about the direction or orientation of the force. These three things are all going to factor into torque. And we're going to put them together on Thursday into an equation. So let's knock off there. Okay, you at least have enough information to open the door and leave the room. Okay.